Hello, everyone. I'm Nicky Ringland. I'm from the Google Open Source Security team, and I'm going to talk about everyone's favorite, dependency management. And I have to give a massive shout out to Adam Harvey, who gave me the best possible setup. If you didn't watch his talk, watch it later. It's fantastic. All right, so here you are. We're working on our awesome project, and you find yourself installing a dependency. That's amazing. But what even was that? What did you just install? At deps.dev, we've been working on understanding open source package management ecosystems for more than 6 years. And in that time, a key thing that we found is open source dependencies are much more complicated than we ever appreciated. You can think of this talk as an abridged version of my learning process. You're welcome / apologies. But before I get into it, let me give you a bit more context about what deps.dev is. We work on all of these fabulous projects, Salsa, OSV, deps.dev, and the security scorecards that I got a shout out in the last talk. Indeed, everything we do is best effort. It turns out this space is ridiculously hard. And we look at deps.dev, we look at open source dependency management with the aim of helping consumers and maintainers better understand and work with their dependencies. So we collect and analyze data about millions of open source packages from across NPM, Go, Maven, PyPI, NuGet, and Cargo ecosystems. And we make this data freely available via a website, via a BigQuery dataset, and a free API. So why does deps.dev care so much about understanding open source dependencies? Well, it turns out because open source dependencies literally run the world. More than 95% of commercial software depends on open source, basically everyone. Now, it's hard to say that the use of open source is growing because it is basically already everyone, but we can say that open source itself is growing. From Sonatype's State of the Software Supply Chain 2024, PyPI grew by 10% in terms of numbers of packages and about 30% in year-on-year downloads. And while it's great that we have so many new packages to use in our projects, it's also really important to balance the benefits that we get from open source software with the risks associated with depending on source code that's largely out of our control. And this is something that we actually don't seem to be doing really well. That same Sonatype report reveals that 1 in 8 open source downloads has a known risk associated with it. And 2.1 billion Java components with known vulnerabilities are downloaded every month. And what's even more startling is that of those 2.1 billion downloads, nearly 96% could have been avoided as a better fixed version was already available. We see these patterns play out across many different ecosystems where users are continuing to download and use vulnerable package versions. But why is this so hard to get right? It sounds like this should be pretty simple. Surely, when I'm using a package, I can just check if it or any of its dependencies are vulnerable, and if they are, I just don't download it. Even for packages with lots of dependencies, this should be easier now than ever before because we have standards like the Software Bill of Materials, SBOMs. That's right, I did just drop an SBOM. You can think of an SBOM like a sort of recipe. If you wanted to bake a cake, you might look at the recipe, which would have a list of ingredients, all the ingredients that make it up, and then the instructions for how to combine them. In a similar way, an SBOM inventory is all the ingredients that make up a software component. So an open source package and the processes that were used to build that package. So the intention is to make it easy for the user to figure out what security and legal risks might be associated when consuming a piece of software. But unfortunately, even with SBOMs, knowing what dependencies I'm actually going to get when I install that open source library is not as easy as it sounds. To see why, let's look at an example from the package management ecosystem NPM. Wait, why NPM? I'm at a Python conference. Well, it turns out that I have skilled up in language ecosystems that have had fairly catastrophic security problems recently. And Python isn't one of them. But if you feel left out, remember that you in the audience have the power to change this, but please don't. So, this is the deps.dev page for the npm data visualization package D3. Over 2.3 million users download D3 each week, and some weeks that includes us, because we use this for our graph visualizations on the deps.dev website. You can see here that the latest version of D3 has no security advisories. That means that D3 itself doesn't have any security advisories, and also that the dependencies of D3, as resolved by deps.dev, don't have any security advisories either. But, unfortunately, knowing whether or not if I install D3, that I won't be installing any vulnerable packages is not that simple. To understand why, let's take a closer look at D3's direct dependencies. So, D3 itself depends on 30 other open source packages with the following requirements. When we download D3 to use in our project, our package management tool, which would be npm in this case, it looks at these requirements and it resolves them into the specific versions of those packages. But it doesn't just look at the requirements of D3, because while a package like D3 has direct dependencies, those dependencies also have their own dependencies, which have their own dependencies, and so on. So, note on terminology: direct dependencies, indirect or transitive dependencies. So, those 30 direct dependencies on the left there, each of those potentially has their own dependencies, and everything gets resolved in a specific way, more on that later, and we end up with a graph on the right, combining all of them. I like looking for the hidden animals. I reckon this one's a frill-necked lizard, but aside. These are all of the direct and the indirect dependencies. For those of you with excellent eyesight, the giant screen helps, this is a total of 37 dependencies to install, but that's just for us. There are 2.3 million other users who download D3 each week. And due to some quirks, foreshadowing intensifies, they may well end up with a different graph. Okay, well, what do you mean different graphs? How many different graphs are there? If you haven't spent multiple years agonizing over the intricacies of open source dependencies, then that might seem like a strange question. It would seem obvious that all of these users should get exactly the same set of dependencies. It's pretty intuitive and sensible to think that. That's what we assumed when we first started the project, and that thinking underlies the idea of producing SBOMs for open source libraries. But there are actually zillions of valid dependency graphs for D3. We calculated approximately that number, so on the order of 10 to the 81. These are the valid graphs that meet all of D3's dependency requirements, which is approximately almost the number of atoms in the universe. Yeah, okay, so, as we'll see later, there are intentional and good reasons to have multiple valid dependency graphs. But what this means is that if you're the maintainer of a project, you're probably managing more than one dependency graph, even if you don't necessarily realize you are. And a different dependency graph means a different attack surface, different behavior, a different set of vulnerabilities, different licenses. So, what are we doing here? And for the rest of the talk, let's look more at what dependency resolution actually is. Answer, why so many graphs? Look at what this means for open source security standards using SBOMs as a case study. And finally, we'll all have a cry over some dependency management best practice recommendations. All right, dependency resolution, how does it work? Most high-level languages allow users to reuse code. This is generally considered a good thing. What all these various language import statements are saying is that there is some code library somewhere else that I want to use. So how do I get it? Well, back in the day, that code was manually obtained and put somewhere near your code, and then you'd import that file directly. This does not scale nicely, and sometimes that's a problem because remember old mate here? D3, well, you might get a graph that looks like this, or maybe one that looks like this. This one is for the dependency graph for Kubernetes 129.3. For this sort of graph, we're going to need some tools to help. In general, these tools they don't look at the import statements directly, but they look at special files instead. So in NPM, this file is called a package.json. It contains a list of package dependencies and requirements for each of these. Versions in open source packages, for the most part, somewhat resemble Semver 2.0 form. You have a major, minor, patch part, and an optional pre-release part. But while versions usually resemble Semver, requirements come in all different forms. And there are heaps of different operators that exist across different package management ecosystems, all with their own special, unique meanings. But requirements generally specify a range of accepted versions. For example, in NPM, the caret operator is used extensively, and caret 16.13.1 means to accept versions greater than or equal to 16.13.1, but still with a major part 16. Some requirements can also specify a preferred ordering on accepted versions. So for the caret operator, later versions are preferred. Foreshadowing intensifiers. A tool like NPM looks at these package dependencies along with their requirements and chooses a version that satisfies each of them. And it handles downloading that for the registry as well. But then actually choosing a version for each dependency is more complicated than that because dependencies have dependencies and so on. So dependency resolution is taking a set of version requirements, choosing a valid graph of those package versions that satisfies all of those constraints. Phew. All right. So that doesn't seem like an atoms of the universe size problem, surely. Well, there are a few things going on here. Dependencies aren't resolved in isolation. So your project probably doesn't depend just on one package. On average, NPM projects average about more than 100 dependencies, whereas for Python, it's a much more manageable 10 or so. I should note that this is for libraries themselves. If you're writing an application, the numbers are generally much higher. But regardless, your direct and indirect dependencies can often have complex relationships between them. And generally, fewer dependencies makes things easier to handle. So how does the resolution algorithm pick a version? Like many things in dependency management, it depends. So for Python, here's what the pip tool does when resolving b greater than or equal to 1 on its own. It picks the latest version that matches all requirements, 1.0.2. But what if I also depend on some package X, and maybe X also depends on B? Well, we now need to choose a version of B that respects both of these constraints. And those constraints combined, well, there's only one valid version of B that we can choose, and that's 1.0.1. Great. Both of these constraints are satisfied, they've found a compromise, everyone's happy. But this is handled differently in other ecosystems. Because in NPM, we don't need to compromise, we just install multiple versions. Easy. So rather than combining these constraints together, the package B would be installed twice at different versions. So here we go, side by side. Who wore it better? There's no clear winner. But note that by installing B greater than 1.0.0 in isolation, got us a different version of package B than when we resolved it in the context of other dependencies. So here's an example of a real Maven package where it really mattered that the dependencies weren't resolved in isolation. This is a snippet of the dependency graph for Maven package vert data real data, and you can view it on the deps.dev website. There's a lot going on in this graph, so I've simplified it just to the relevant slide parts here. So vert data imports many dependencies, one of them being log4j core. Now, some versions of log4j core are affected by the log4shell vulnerability, which some of you may remember from the summer of 2021. The version 2.0 alpha 2 is affected, but version 2.14.1 is not. Now, vert data isn't just depending on log4j once, it's depending on it through 5 different packages. 4 of these use 2.14.1, and one of them is using the requirement to 0 alpha 2. So a plain version requirement in Maven means select that version unless a lower requirement exists, and since 2.0 alpha 2 is lower than 2.14.1, unfortunately this is the version chosen by the tool. And the fact that there are 4 other requirements that asked for a different version that wasn't affected by the security vulnerability didn't matter, because there was one plain version requirement lower than it. So resolving it in the context of alpha 2 requirement gives us a different result to resolving it, the 2.14.1 requirement, in isolation. Another complexity we see in deps.dev is that dependency resolutions change over time. So recall that a dependency requirement can have many possible answers. Now, each of these is a valid choice. Tools like Maven, Go, and NuGet choose the lowest version possible for the given constraint. Now, the philosophy there is that I don't want my dependencies to change underneath me. I'll only get new features, new fixes, and bugs when I choose to update my dependencies. So I know to be on the lookout. But on the other hand, other tools like npm, cargo, and pip choose the latest available version, which lets projects pick up the latest fixes and features automatically upon re-resolution. But this also impacts the number of possible resolutions. So as new versions are published, a new dependency set is possible when re-resolving, and then, remember, the updated version of B may also have an entirely new set of dependencies as well. So how often do we see these packages changing? Here's the proportion of versions within the PyPI and npm ecosystems that have had a graph change each day over March this year. And you can see that it varies from just a few to 25%. That's a quarter of all package versions of all packages having a different resolution result to the day before. That is a lot of change to get your head around. So, next thing is multiple tools. Language ecosystems can have multiple tools. There's npm and yarn, or pip and poetry and uv. Now, these tools can differ in how they work through the resolution constraints. And there are lots of different decisions when we're resolving these graphs. Whether it's okay to install dependencies twice, choose the lowest or highest version, changing how to backtrack through the graph, whether to prefer constraints closer or further away from the root of the graph, even the order in which these constraints are worked through, that changes things. These things can make a really big difference. Take these package JSON for a node project. There are 4 dependencies specified here, and 2 of those are using aliasing. They alias a package name and a requirement. Think import blah as foo. So let's look at these graphs. This one was with npm 6.14.13. This one is resolved with yarn 1.22.10. You can see that intern map is now being installed twice. And here's pnpm 8.6.9. The intern map dependency has disappeared altogether. So we've got 3 tools producing 3 different graphs, and they handle these requirement files differently. And then the tools can also change. Back in 2014, the NuGet team made a change to patch selection, essentially changing from preferencing the lowest version but the highest patch to the lowest version for all parts, major, minor, and patch. The reasoning behind this change is that it would increase the chance that you'd get the same result upon running the tool again. NuGet has since made even more changes, and this is normal. We see this across all the tools we analyze in deps.dev. But NuGet gets a shout out here because NuGet is great at announcing and documenting these changes, which makes our life much easier. Thank you. So finally, your system architecture can also change your dependency graph. Let's say I'm writing a project and I want to import the Python package TensorFlow, the Python TensorFlow library. The latest release is 2.16.1, so that's what I install. But PyPI package versions are spread across multiple distributions, which can be specific to operating systems or CPU architectures. And while I'd like to use the same import statement regardless of the platform I'm using, when I install TensorFlow on Windows, the pip tool automatically selects the Win AMD 64 distribution of the TensorFlow version. But if a friend were to install the same version on her Linux machine, she'd obviously get the Linux distro. And the dependencies for these distributions can clearly be quite different. You can see one is definitely shorter than the other, for one thing. The maintainer of these packages may be taking good care of their dependencies on the platform that they're developing in, but maybe they don't actually think to address the issues, or they don't preference them on the Linux dependency graph. This might also happen if we're developing software in an environment that's different from our production environment where it ends up running. Let's say I'm a developer working in macOS, and I'm writing code that gets run on Linux production servers. When I build my program on my macOS computer, I'll get a set of dependencies, some of which may be unique to macOS. But when my code gets pushed to production, it's being built for the Linux production environment, which means that its resolution graph won't include any Mac-specific dependencies, but might include Linux-specific dependencies that never appeared in my development graph. And these new dependencies might bring new security vulnerabilities that weren't present in my development environment. And this can lead to a really horrible situation, because being the responsible open source consumers that we are, we may be running all of the vulnerability scanners that we want within our development environment, but we still won't be able to detect these vulnerabilities because it just doesn't exist in our dependency, in our development graph. It only exists in the production graph. So it's absolutely crucial to scan not just what's running on your development environment, but also what you're actually deploying to production. And it's also important to try and make your development environment as close to your production one as possible, where possible. So, back to our number. All of these reasons were designed with intent. They each exist for a good purpose. We want to be able to install more than one dependency. We benefit from improvements to existing tools, and the fact that open source communities are strong enough to have alternate tools is a fantastic thing. And there are so many more reasons as well. But the takeaway here is that it's dependency graphs, not graph. So, now we know that it's not really correct to talk about the dependency graph, the one true dependency graph to rule them all, for an open source library. What does this mean for open source security standards like SBOMs? Well, we remember our SBOMs, right? Tasty cake. There are many different specific SBOM standards out there. For this, I'm going to use a simplified representative SBOM format that I made up that fits on the slides. So, let's walk through an ideal case of an SBOM. Let's say I'm distributing an executable application. To help my users feel confident in knowing what they're installing and running, I make an SBOM, and I include all of the components that went into building it, so that anyone who wants to can manually look at those components or scan them for vulnerabilities or licensing risks, etc. We can see in this scenario, an SBOM is a really good standard that makes parts of the piece of software transparent to end users. But things get complicated when we're constructing SBOMs for open source libraries. Let's say my friend Josie has been working on a library and I really want to use it, so I suggest that she publishes it as an open source package. And she does. And as a responsible open source maintainer, Josie decides that she should publish a release of the package with an SBOM for her library to let others know what components went into building it. When she goes to build the release, the tools will perform dependency resolution. Now, the library only has two dependencies on other open source packages, package A and B. And there's only one package of A available at the time of publish, so the resolver picks that version. There are two versions of B available, and let's say we're using a resolution algorithm like pip or npm that picks the latest version, so we'll end up getting the newer B at 201. So all of that information goes into Josie's SBOM, and as you can see, none of the dependencies have a vulnerability, so that's great. Now that Josie's library is published, I'll have a look at the SBOM, see that there are no issues, so we're good to go. All right, so as well as depending on Josie's library, my package also depends on another package, X. So when I go to build my project, I'm going to have to look at both the dependencies of Josie's library and the dependencies of X. Neither of them have many dependencies, but both have a dependency on package B. But first, let's resolve the dependence on package A. All right, so since Josie published her package, some time has passed, and the maintainer has actually published a new version. Because we're working in an ecosystem that picks the latest version that matches the requirement, we're going to pick that new version 101. And this new version of A, this adds another dependency on package C, so we'll get that too. Great. Then we come to resolve our 2 requirements on package B. And because of that specification from package X, I'm actually going to get version 2.0.0 of B. So let's compare. These 2 graphs are totally different. We don't depend on any of the same versions of packages A and B, and Josie's library doesn't pull in the additional package C. I didn't get any of the dependencies that Josie's SBOM said that I would. You can see that basically every single important line from our original SBOM ended up basically being irrelevant. So any license or any vulnerability scanning I performed on the library's SBOM wouldn't have been useful at all. This is not to say that the SBOM was wrong. It accurately described what Josie got when she built her library, but from my perspective and my resolution context, it was meaningless. So, are SBOMs bad? Should they feel bad? And should we not use them? No, we should use them, but they're for applications, not for libraries. And it's not just SBOMs. Lock files, for example, suffer from the same problem. It's helpful to lock your dependencies for your project. It's helpful to lock those dependencies for your project, but the lock files for any dependencies you won't be used by your tool. And that's for a good reason. The tools don't consider dependency lock files because users of their libraries often need more flexibility when dealing with their requirements. Essentially, the dependency graph you get when installing a library will be unique to your resolution context. To help you grapple with this complexity, let's end on some dependency management best practice. Whew. All right. Dependency management, like all aspects of engineering, requires careful thought and judgment. We do code review, we do unit testing, integration testing, pre-submit testing on code that we wrote. But how often do we apply that level of rigor when assessing the code that belongs to our dependencies? When we're using a dependency, there are trade-offs and many factors specific to your project situation that you need to balance. Dependencies are essentially a trust relationship. And you need to trust them, but you need to do it with an informed mind. So, some practical recommendations. Don't write software. Just don't do it. Rocks were not meant to think. It was perhaps a mistake. If this one doesn't work for you, if you have to, maybe instead consider the cost of each of your dependencies that you're bringing in. Remember that when you're importing a dependency, you're signing up to maintain it. That's right, you are going to be the one essentially responsible for using it and all of its dependencies. Perhaps as the Go proverb goes, a little copying is better than a little dependency. Left pad. Secondly, you should scan what you ship. Scan your dependencies in context. Look at your dependencies when you actually install a library, and if the graph that you're running your vulnerability scanner on isn't the one that's being used in production, then your scans won't be very useful. So try and make your development environment as close to production as possible. For library authors, keep your requirements open. Pin your applications, not your libraries. Publish clear metadata, not SBOMs, for libraries. So we need things like authorship, contact information, where to file bug reports, a clear license for the library. And finally, for ecosystem maintainers, provide simple and predictable tools that help people understand their dependency graphs, because dependency resolution and management is incredibly complex. This is hard. Good tools are awesome, and the people who make them are even more awesome. So keep being awesome. And in fact, that applies to open source consumers and maintainers as well. All right, if you're interested in building tools using our data to help with this problem, the deps.dev data is freely available through the website, through the API, and the BigQuery dataset. Please go and make some cool stuff and tell us about it. I'd love to be excited for you and for us. If you're interested in reading more, I can recommend a blog post. You can find it at blog.deps.dev/zillions of SBOMs. Thank you very much.